Colin, do you want to? I'm very happy that today we have Professor Haizhao Yang giving a talk at our 1W-MINDS seminar. Haizhao is currently a visiting professor at the Department of Mathematics at the University of Maryland, College Park. Before that, he was at Purdue, and before that, he was at the National University of Singapore. He had a visiting assistant professor at Duke University, and he got his PhD from Stanford before that. Haizhao has won lots of awards, including the Young Investigator Award from ONR, the Career Award, and many others. And we're very happy to have him talk to us about discretization-invariant operator learning. So the floor is yours.
Thank you very much for the invitation. It's my great pleasure to have the opportunity to share my recent research in operator learning. I will talk about some algorithms, including their theory to support the algorithm. Why operator learning in scientific computing? Because in many problems in scientific computing, we want to learn some mathematical operator between some function spaces. For example, in reduced order modeling, we typically have a high-dimensional system, which is very expensive to solve. So we want to build a low-dimensional system such that we can essentially solve the low-dimensional one to get information about the high-dimensional one. So if we want to build some low-dimensional system, then we want to learn the operators to build that system. In solving some parametric PDE, for another example, we have an operator mapping from the parameters of the PDE to the solution of the PDE. So if we have learned this operator, then we can have a very efficient way to solve parametric PDE, in the sense that if you have a new parameters function in the PDE, then you just input it into your learning algorithm, it can efficiently output the solution of the PDE. Typically, we can build a neural network to learn this operator so that you can just apply neural network once, then you can solve the PDE. And in some other problems, for example, solving inverse problem, we have some mathematical operator mapping from the measurement space to the image space that you want to reconstruct, including face retrieval, including image processing, where we have mapping from some data to the image of interest. In predictive data science, we want to have mathematical operator mapping from the historical data to the future data for prediction. Typically, in all these problems, the interesting mapping are high dimensional or even infinite dimensional, mapping from some function space to another function space. So training some neural network for solving this problem is quite challenging, especially in real application. We care about good accuracy at low cost. So if we don't have discretization-invariant in this learning algorithm, then whenever you have different data structure in your testing, then you might have to repeat to train the neural network again so that you can apply the new testing data in your neural network. The repeated training might be very expensive. So this motivates the work for discretization-invariant operator learning, such that we hope to train the neural network once, then in all other, for the application, for all other data structures, we can still apply the trained network to these data structures. So this is the main goal of today's talk. Mathematical speaking, we have a known operator psi between two function space x and y. We don't know this operator, but we have some samples generated by this operator. For example, we might have some functions ui and vi. The vi is generated by the operator psi with ui as input with some possible noise. Our goal here is to learn this unknown operator psi from the finitely many samples. Typically, we might want to build a deep neural network psi n to parameterize the unknown operator psi, we want to find the parameters of this neural network such that it can approximate the unknown operator very well for all the possible samples, U and V pairs. If we use some naive neural network to solve this learning problem, then maybe we don't have the discretization invariant due to the structure of the neural network. For example, a fully connected neural network can be summarized using the mathematical formula here. We have the composition of some simple nonlinear function denoted by hi. And finally, we have a linear transformation T applied to the output of HL. We build a nonlinear function hi using the composition of a linear function with coefficients W and some bias vector B, and a nonlinear activation function entry-wise applied to the resulting vector here. We can use some figure, for example, the figure here, to visualize the computational flow in the mathematical formula here. Given an input vector U, we apply a sequence of linear transformation in hi and a sequence of nonlinear activation function. Then finally, we have an output vector V. So from this figure, you can clearly see that if you have to fix the size of the vector. If you have different size of the vector, then you might have to have different sizes in the linear transformation, which means that you might need to have different vectors to handle different sizes in the input and output vectors, U and V. So in practice, if you use this kind of fully connected neural network to learn an operator, then it means that you have to fix the size. But in real application, sometimes due to some different discretization format, you might have different vector sizes representing the interesting function you want to apply. So this means that this fully connected neural network is not discretization invariant. And today I'm going to talk about some new technique to make deep learning discretization invariant for operator learning.
Haizhao,
yes.
I think we have a clarification question from the audience. Tian Jiao wants to know what you mean precisely by discretization.
Okay, I will discuss the discretization here. For example, the learning object is to learn some operator between some function space x and y. So the original goal is that given a function u, you can build a mapping that map the u to the target function v in y. But in practice, in computer, we have to discretize that to do the computation. For example, in traditional way, you can use some sampling technique to sample this function on some sampling grid points to get a finite dimensional vector to represent this function. And this is what the method mentioned in the question. And you can also use some other algorithm to do this sampling. I call it encoder, to encode a function to a finite dimensional vector. For example, you can also use basis expansion. Like given the function, you can use the Fourier transformation to transform it to the frequency domain. You can truncate the high frequency modes and only use a low frequency coefficient to get a vector to represent the original function u with some truncation error. You can also use PCA with some data adaptive basis function to do the expansion. Does this answer your question?
I think so. Thank you.
Okay. We have encoder to encode a function into a finite dimensional vector. And at the same time, we also have the decoder to decode a finite dimensional vector to a function v. So if you use this encoder and decoder, then the original learning problem from u to v is reduced to a learning problem from a finite dimensional vector in Rdx to another finite dimensional vector in Rdy. So in those naive algorithms without discretization invariant, you might want to use a fixed size free connecting neural network in the middle, so that you want to learn a free connecting neural network mapping from the finite dimensional space to another finite dimensional space. But if you have, in practice, if you have different discretization algorithm resulting in different sizes in these vectors, then you have to have different free connecting neural network for the purpose of handling all kinds of discretization formats. So if you have to repeatedly train many different fixed size free connecting neural network, then the learning is expensive. Today, I'm going to introduce some idea to get discretization invariant. Actually, the idea is very simple, and we can just use one single slide to illustrate that. But before that, let me state the goal in our discretization invariant learning. First of all, we will design some encoding and decoding scheme such that we, no matter, actually you have function u, but in practice you won't really have a function u. You might have a vector of different sizes coming from all the possible discretization format you might have used to discretize the function u. So I want to have some discretization invariant encoder in the sense that no matter what discretization format you use to discretize this function u, this encoder can encode the vector to a fixed size vector without loss of much information. And at the same time, we want to have a discretization invariant decoder in the sense that it can decode a fixed size vector back to any arbitrary discretization format you want to use without much loss of the information. So we want to have discretization invariant encoder and decoder. Second, the second main point is that the learning problem, it looks like it's from infinite dimensional function space X to another infinite dimensional function space Y. It looks very challenging because of the curse of dimensionality. And my feeling is that in many applications, actually the dimension is not very large. Probably we can have a finite dimensional truncation to truncate this problem, to reduce it to some easier to learn low dimensional problem. If the problem itself has some low dimensional structure or low complexity structure. So if we have this structure, then we want to have some data-driven encoder decoder that can capture this structure to maintain good accuracy in the learning. If we talk about this kind of learning, probably we can use sparsity terminology to talk about that in compressive sensing. We want to have encoder to compress something and process it, and then you use decoder to decode the information back to the original function space you want to get. And this is these two main points. In the middle, I would like to use neural network because we believe that neural network has very good approximation power, such that it can learn complicated nonlinear mapping in between these two vector spaces. So in the next slide, I will illustrate the main idea to get discretization invariant. And then I will briefly talk about why we believe that we can capture the intrinsic dimension of the problem. The idea to get discretization invariant is to use integral transformation. Why integral transformation can get discretization invariant? Because no matter how you discretize the input function u, well, we want to have an integral transformation to represent some mapping from a function u to another function v with discretization invariant, in the sense that no matter how you discretize the function u and how you discretize the function v, as long as you have an integral kernel possibly parameterized with a neural network with parameter theta. Then you can evaluate this kernel function phi according to your sampling in X and your sampling in Y to get a matrix, so that this integral can be computed through the matrix vector multiplication. So no matter how you discretize U and V, we can still carry out this computation to carry out the mapping from U to V. So in this sense, it is discretization invariant. You might wonder why I want to emphasize nonlinear integral transformation here, because according to our numerical experiments, adding U to the kernel function resulting in the nonlinearity, which can help us to improve the learning accuracy, as we shall see in the numerical section. And the second way to interpret this nonlinear integral transformation is that we can think about this as a data-driven way to learn some powerful integral transformation that have been very useful in data science and machine learning. For example, we can prove that if we use neural network to parameterize the function, that it takes some parameter theta to approximate typical integral transformation with high accuracy. For example, like Fourier transform, Wave-free transform, or other integral transforms that might be interesting. And you can also interpret this integral transformation as some deep neural network-based PCA, in the sense that we use neural network to parameterize the basis function. In PCA, once you have built the basis function, then if you use this basis function to project it to the coefficient space, then you just simply do the matrix vector multiplication, apply it to input function U, then you can get a coefficient V. So you can also understand that we try to use neural network to build a basis function in PCA, but in practice, we don't train the neural network with some orthogonal constraint. That's the only difference. So this is the idea for discretization invariant, and we hope that we use data-driven neural network as kernel function, such that we can train some advanced kernel that can capture the intrinsic sparsity structure of the function, so that probably U might look very complicated, but after some transform, we can get some simple short vector V to represent all the information of interest contained in the function U, so that we can use a fixed size neural network in the middle to learn something. This is the main idea. I see we have a question in chat.
We took care of that.
Okay.
Oh, I see. There's a new one. I'm sorry.
Yeah, a new one. So after the integral transform, we should still be the function of theta, which is discretization invariant. It is discretization invariant in this. Well, theta is a fix. So after learning, theta is a fixed parameter. So you don't think theta is a parameter of this function V. And it is discretization invariant in the sense that no matter how you want to discretize V, we can still carry out the integral transformation to match your discretization. For example, you can train using data like sampling grid point like of size 100 in Y. And if you want to get some reconstruction result with grid size like 1000, then that's fine. You just use your 1000 grid point to discretize this V. We can accordingly evaluate a matrix to carry out a transformation to match your requirement. Does this answer your question? Okay, now then next I'm going to introduce the second idea to build our final network to get the discretization invariant operator learning. So we have illustrated the basic idea of encoder, fixed size neural network, and decoder. We are going to use this as a basic structure to build a wider and deeper network. And why we want to build a a wider network in parallel with several blocks in parallel. The idea is that sometimes it is easy to learn in the original function domain, and sometimes it might be easier to learn in the transform domain. For example, maybe some data might be sparse in the after Fourier transformation or wavelet transformation, so that if you learn in the transform domain, it is easier to get something useful. So this motivates us to use this encoder-decoder structure in parallel for several blocks. Given the input function here, we use the original signal for one block. We do Fourier transformation and input the coefficients into the second block. After the encoder-decoder structure, we perform Fourier inverse transformation to transform it back to the spatial domain and add it to the result learned from the original input. If you want, you can also add some other transform to form a wider neural network. After adding all the results together, we use a very small neural network to post-process the information. And finally, we want to compose this block in blue and red, sorry, in green and red together to form a deeper neural network. There are several ways to form the composition. We can either use a Fourier connected neural network idea. We can also use a ResNet structure. We can also use densely connected neural network, the DenseNet idea. In our numerical experiments, we can show that using DenseNet idea to add many skip connections between these layers can better reduce the test accuracy, improve the test accuracy. And the third idea, which is also a key idea in our algorithm to achieve discretization-invariant, is to do data augmentation. It is kind of difficult to believe that if you just train a neural network using a fixed discretization format, then you can get good generalization to other discretization format. At least when I do this problem, it is quite challenging for me to accept this fact. So this motivates me to think about some idea that can make me easier to accept this fact, is to do some random data augmentation. The idea is very simple. Suppose psi is the network that we built to do the operator learning. Given an input U, we want to learn a network psi such that it can map it to a target function V. Here, L is some loss function, for example, the mean square error. And in our optimization procedure, we want to have some random interpolation operator S, such that we can interpret some given training data with a fixed discretization format to some other discretization format. For example, suppose all the training data are given with 100 sample grid points in U and 100 sample grid point in V. Then we randomly interpret these samples to larger or smaller grid sizes to get some other discretization format. And we also put this discretization format into our training procedure through the regularization term here, such that we want to enforce the neural network side can see many other discretization format. So if we apply all the ideas together, then we can get our final algorithm called integral autoencoder neural network. And we try to compare our integral autoencoder neural network with some existing algorithm to see the performance. We compare it with some discretization-invariant learning, for example, FNO and the Fourier transformer, Garankian transformer. We also compare it with some other algorithm that is not discretization-invariant, for example, the UNet for signal processing and the DeepONet. The original DeepONet is not discretization-invariant in the input. So in our algorithm, we need to repeatedly train the deep neural net again if we have different grid sizes in the test data. We are going to compare our algorithm with these algorithms in 4 different kinds of examples, like prediction, solving forward inverse problems, solving some signal processing problems. The first example is a typical example in the discretization-invariant operator learning papers. It is a Burger's equation. We want to learn the mapping from the initial condition, to the solution at a future time step, for example, t equal to 1. Essentially all the algorithm can achieve discretization invariant with relatively good accuracy. So if we check the tables here, we compare the FNO, FT, GT, deep neural net, and also a very naive algorithm where we have a fixed size ResNet, and we use some interpolation technique as before the input of the ResNet and after the output of the ResNet to deal with different discretization format. For example, if you train it with some function with only 100 grid sizes, then the input size of the ResNet is 100. In the application, if you have a function of size like 200, we can naively use interpolation to interpret the vector of size 200 back to the vector of size 100 so that we can apply this ResNet. So this naive algorithm is called ResNet plus interpolation. And we have also compared our algorithm with different kinds of choices as we have several ideas to build our integral autoencoder neural network. So the so-called no-DA is the algorithm without data augmentation. No-skip means that we use a fully connected idea to build a deeper neural network. ResNet here means that we use the ResNet structure to build deeper network. And the final IAE net is the network that use denseNet structure. So according to the figure here, we use a grid size like 1024 to train FNO, FT, GT, and the ResNet and all the IAE net. And then we test them using other grid sizes. For deep neural net, we have to repeat the training because it is not discretization invariant in the input. So as we can see, the accuracy here, FNO, FT, GT, ResNet plus interpolation, and almost all the IAE net version can achieve discretization invariant. According to the comparison here, IAE net, our final version IAE net can achieve the best accuracy. This is in my opinion, this is not a very challenging example because you might argue that probably you need to choose different new because the new might significantly increase the difficulty in the learning. That this is true. If we have different new, then the accuracy might be quite different. In our paper, we have tried to test our accuracy using different new, and we can prove that we can achieve discretization invariant. But for different new, we might have different level of accuracy in the learning. The second example is the example, also a typical example in the literature. It's a 2D Darcy flow equation. This is a parametric PDE problem. We want to learn a mapping from the parameter function A to the solution function U, so assuming that F is fixed. Next, we compare different algorithms, and we can see that the IAE net is also the best among all the other algorithms. It is also interesting to see that the naive algorithm, which is a ResNet plus interpolation, can also achieve very good accuracy with a line here, achieving the discretization invariant. So probably the first two examples, there might be some simple example such that it's easier to get discretization invariant. It's such that you can easily use a fixed size ResNet plus naive interpolation to achieve discretization invariant. So you might wonder whether we have some example to show that this naive algorithm will fail. So this motivates our work to test some more challenging problem. For example, use learn the operator that can solve the inverse scattering problem. In this problem, we have the Helmholtz equation where the frequency omega is given. We want to learn the velocity function c from the measurement of the solution u. So essentially we have operator mapping from the measurement of u to the function c. In application, typically we have some background about the function c. So we assume that we have a known function c now, such that we can do the decomposition here. So learning c is equivalent to learn the eta function. So if we substitute this function back to the Helmholtz equation, then we can get a new PDE model here, where L now is a non-operator. So the problem is reduced to learn the eta function from the measurement of the solution function u. We apply different algorithms to solve this problem and to see whether we can have discretization invariant. So we try to have some training data coming from the solution of this inverse scattering problem. And we train the neural network with grid size 81 and apply the trained neural network with some other grid sizes. So you can see that IAE-NET can still roughly achieve discretization invariant in the sense that the error level is almost the same. And for the other algorithms, the accuracy can be much worse than the accuracy they are when the grid size is trained. So we can clearly see some V shape for the other algorithms. So this is one challenging example, such that the naive ResNet plus interpolation cannot work. We can still see some V shape for this naive algorithm. As for the last example, we have an example. Oh, we have a question for example 3. What is the boundary of example 3? We put sensors around the boundary of the solution U. So we assume that we know the solution U at the boundary of the domain, and we want to get the information of eta. And in the last example, we have some example for signal processing. We try to apply this algorithm to learn the operator for solving a blind source separation problem, where we have a signal coming from the ECG measurement from mother. The signal might contain several information. For example, the information of the fetus, and also the information of the mother herself, and possibly some noise. So our goal in this problem is to decompose a given signal into 3 components corresponding to the mother ECG, the fetus ECG, and some possible noise. We try to apply all these algorithms to learn the mapping that map one single signal into 3 different signals and try to test the accuracy. As you can see in this table, the IAE-NET, the final version of the IAE-NET can essentially achieve discretization invariant. But if you look at the other algorithms, the accuracies are quite poor. So this is the end of the algorithm part. We have one more question in the Q&A. Are you able to quantify how the error grows with over sampling factor ratio of signal dimension. If I understand correctly, you care about the dimension of the signal. You wonder if we increase the dimension of the signal, whether we have poor accuracy. Is that correct? In our theoretical results, we can clearly see that the dimension of the signal matters. If we have larger dimension, then the accuracy will become poor. And in all the numerical example we have tested, we have low dimensional signal. For example, in this example, we have a one-dimensional signal. In this example, we have two-dimensional. In this example, we have two, and in this example, we have one. In practice, if we have a function, high-dimensional function, and we want to learn an operator acting on a high-dimensional function, I think this is very challenging because when you try to use some vector to represent this high-dimensional function, you already have the curse of dimensionality. So to the best of my knowledge, there's no successful application for this kind of operator learning algorithm for high-dimensional functions. If I'm wrong, please correct me and send me some reference. Thank you. So the second part is to discuss the accuracy of this kind of operator learning algorithm. And you can also see the role of dimensionality in the learning accuracy. To the best of my knowledge, we can only find two recent papers on this object. The first one is developed by the DeepONet. For the DeepONet, it is a posteriori error analysis. And the second one is for learning linear operators using some traditional learning algorithm without deep neural network. So our goal is to see whether we can develop some theoretical investigation for a priori error analysis for learning nonlinear operators with discretization-invariant. We focus on the learning algorithm with the basic structure here, because as you can see in my slide, this basic structure it's the basic component to build our wider and deeper neural network. So once we can understand the theoretical performance of a learning algorithm with this basic structure, we can extend the analysis to analyze more complicated neural networks. So in the theoretical analysis, we focus on this basic structure, where we have encoder, decoder, and fixed size neural network. Actually, this basic structure has already covered several examples in operator learning. For example, if you use the naive ResNet plus interpolation, this means that in the middle, you have a ResNet structure. In the encoder and decoder, you have some interpolation technique to deal with these different kinds of discretization formats. This basic structure also covers the PCA network for learning operator, because you can use PCA to build the encoder and decoder. And you have a fixed size neural network in middle to get some operator learning algorithm. You can also think about this basic structure as a DeepONet, where the encoder is some sampling algorithm and the decoder it's a neural network-based PCA. Then this basic structure will become the structure in DeepONet. You can also think about the analysis here. It's a special case where we only use a very simple block, only one block in our algorithm to learn the operator. So the mathematical setting for the theoretical investigation is that we assume that the target operator to be learned is elliptic. we have two n samples, the function pairs ui and vi, possibly with some noise. We try to establish some theory for a two-step training algorithm. In the first step, we try to use the first half of samples to learn encoder and decoder in the x and y function space. If you use sampling, if you use basis expansion as the encoder and decoder, then you don't need to learn this encoder decoder because they are given. But if you want to have some data-driven way to get the encoder decoder, like the DNN-based function expansion in DeepNet, like the PCA net, you want to use some data-driven way to get the basis function, then you have to learn the encoder decoder using some samples. In the second step, you use the rest of the training sample to learn a neural network, such that the composition of the encoder, neural network, and decoder can approximate our target operator. We typically use empirical risk optimization to learn this middle neural network. And we try to quantify the learning accuracy in terms of the so-called population risk, considering all the possible distribution of the data. In other words, all the possible function pairs U and V. We wonder if we use these two steps learning algorithm, if we can get the global minimizer. Suppose we can get that, but optimization might be a different story. Suppose that we are able to get the global minimizer of the empirical risk function, then what is the accuracy if we substitute this global minimizer into the population risk? Whether the population risk is small. If the population risk is small, then that means that the learned mapping through the composition here can take care of all the possible data following certain distribution. So in our theoretical investigation, we want to quantify how large the population loss is if we substitute the global minimizer of the empirical loss function into the population risk. We want to quantify the error here in terms of the neural network width, depth, and also the number of samples, because this quantification can help us decide how to choose the network parameters, how to choose the number of samples to achieve a target accuracy. And we especially pay attention to the so-called curse or dimensionality. In other words, whether the size of the network, whether the number of the example might grow exponentially fast when the dimension of the problem increases. We also wonder whether the theory can help us to better understand whether or not we can achieve few-shot or zero-shot generalization for different kinds of data structure. In other words, whether we train the network with a fixed discretization structure can generalize well to other discretization structures. So we apply the typical variance and bias decomposition in statistical learning to decompose the target error into two parts. And in the first part, it is called a bias part, and it can be bounded by analyzing how well a neural network can make sure that the compensation here can approximate a operator. So this means that we can develop some approximation theory for neural network, such that if we can prove the existence of a neural network, such that the composition here can uniformly handle all the samples well, then the error here can be bounded with a small error term. So this is essentially approximation theory for neural network. As for the second one, it is called a generalization analysis. We want to quantify the difference of the empirical loss and the population loss essentially quantify how well when we use the average of n samples here to approximate the expectation. For the approximation theory, we can apply some existing neural network approximation theory to answer the question that how large this T1 would be. Actually, we can apply some existing approximation theory for some given width and given depth to quantify the error. And our attention is whether the curse of dimensionality exists here. Actually, there has been extensive research to understand the approximation theory of deep neural network. For the interest of time, I'm not going to review all of them. We just simply apply some theory that we developed probably 2 years ago to answer this question, because we assume that our operator is Lipschitz. So we apply our theory for using red rule neural network of width n and depth L to approximate a Lipschitz continuum function on a high dimensional domain to get our error bound. So in this result, we can see that for d-dimensional function, if we use the red rule neural network with width n and depth L to approximate a continuum function, the error grows like this. So because of the 1/d factor here, we will have the curse of dimensionality to approximate the d-dimensional function. So this means that we do have the curse of dimensionality. And if we have a target function living on a high dimensional domain, our accuracy will be poor. So this might answer one question for the numerical testing, whether if we have a high dimensional function and we can see that probably the learning accuracy is very poor. Some other problem might be interesting, like if we increase smoothness, whether we can get rid of curse dimensionality, and actually we cannot. How can we get rid of curse dimensionality? If we have some special function structures, or we can use some special activation function, then probably we can lengthen the curse of dimensionality. So as we shall see later in our final version of the theory, if the unknown operator has some low complexity structure, then we can prove that we can get rid of the curse of dimensionality. If the unknown operator is an arbitrary Lipschitz operator, then we cannot get rid of the curse of dimensionality. As for the second part, for the generalization analysis, the literature is quite limited for operator learning, and we apply some existing technique for function learning to build some new theory for operator learning. Essentially, we apply covering number of neural network casts to bound the T2 term, and then we apply pseudo dimension of the neural network cast to bound the covering number. Finally, we use the result for using finite width and finite depth neural network to bound the pseudo dimension of the neural network class of the same width and depth. Combining all the steps together, we can get our final theoretical results. So in this theoretical result, we assume that the unknown operator is Lipschitz continuous. And we try to optimize the width and the depth of the neural network to achieve the best possible learning accuracy in terms of the same number of sample n. So in our final error bound, we have 3 terms. One term characterized in terms of the number of training sample n. For a fixed n, we have some strategy to choose the width and the depth according to the formula here to better achieve the target accuracy here. And the second term and the third term, they're related to the accuracy of the encoder and decoder. So if we want to get very good accuracy, then we need to have good encoder and decoder encode decode the target functions. And we also want to have a very large number of training samples to reduce the first term. The number of training sample is very large because we have the curse of dimensionality due to the dx term, where dx, it is the size of the vector that we use to encode the input function u. So for a function u, typically we might have to have a very large dx to get a discrete representation, such that the encoder, after encoding, we don't lose much information. So because dx is large, we might have to use exponentially larger number of samples in dx to achieve a given accuracy. So we do have the curse of dimensionality here. Second, suppose n is large enough, then we wonder whether we can see that we can prove the few shot or zero shot generalization. So as long as the encoder and decoder for x and y spaces are accurate enough, then no matter how you discretize the function u and output function w, you can still have low error. So this means that we do be able to get zero shot or few shot generalization. So the remaining question is whether we can avoid the curse of dimensionality by assuming some low complexity structure. We consider two special cases. In the first case, we assume that after encoding, all the data of interest lie on a low dimensional manifold in a finite dimensional vector space. For example, d0 is significantly smaller than dx. Then we can prove that instead of having dx, we can have d0 here. So because d0 is small, so we can get rid of the curse of dimensionality. In the second case, we consider the well-known multi-index model to characterize low complexity of some functions in statistical models. So if the unknown operator psi is satisfies some low complexity structure in the sense that after encoding, essentially we have a multi-index model G to characterize this unknown operator psi, then we can prove that instead of having dx, we can still have a small d node in the learning accuracy so that we can get rid of the curse of dimensionality. A very simple example for this low complexity model is that, for example, even though you have a high dimensional function, if this function it's a plane wave in the high dimensional function, actually the intrinsic dimension it's 1D of this high dimensional plane wave, because as long as you know the direction of the propagation, then you know all the information about this plane wave. So that's all for today's presentation. Thank you.